outage. Do you see a flashlight anywhere? Wait, the power outage? What if it lasts forever? What about the food? You know we can find out. How? Well, using heat transfer. We can run some different calculations to find out all sorts of different variables. Namely, we can find out how long the food will last before it spoils. Really? Wow. Yeah, the first thing we have to do is find the dimensions of the fridge. Do you have a tape measure anywhere? Oh, yeah. Here's one. Thank you. So the first thing is we find the height of the fridge, which is 61 inches, 1.55 meters. And the width of the fridge, which is 27 inches, 0.689 meters. And the length of the material of the fridge that the heat will go through, which is 2 inches, 0.0508 meters. And next we find the area that the whole thing will go through, which is the height times the width. And that's 1.063 meters squared. Next we just have to make some assumptions. For example, the temperature of the air inside the fridge is equal to the temperature of the material of the inside of the fridge, and that'll make our calculation a lot easier. Also, we can assume that no heat is lost through the refrigerator while it's on, and that means that it's steady state, and as long as the temperature isn't changing. And that makes our calculation way easier because we can use a different analysis, but only while the appliance is on and maintaining the temperature. Finally, we can assume that the fridge uses polyurethane insulation because we don't know exactly what it uses. But since we don't know much about it, we have to go to the internet. Well, the internet says that it has a thermal conductivity of 0.0245 watts per meter Kelvin. That is perfect. Also, we need to determine the average temperature of a refrigerator because we don't have a thermostat in there. And we need to determine what the unsafe and spoiling temperature of food is. So, the standard temperature of a refrigerator is 1 to 4 degrees Celsius, which is about 275.5 Kelvin. And the average temperature of the freezer is about -18 to -35 degrees Celsius, about 246.5 Kelvin. And the average temperature in which food spoils is about 40 to 140 degrees Fahrenheit, because that's when the bacteria grows most rapidly. And that's about 277.4 Kelvin to 333 Kelvin. But the important thing here is we want to know at the first sign when the food can spoil, which is the lower number, 277.4 Kelvin. Finally, we need to know the temperature of the air outside. Yeah, it's getting pretty hot. Let's see. It's about 90 degrees Fahrenheit, which is 305.2 Kelvin. So next, now that we know all of these numbers, we need to find out the heat transfer coefficient. How do we do that? I didn't see that anywhere. It looks like we're going to have to calculate that. But don't we have other variables? You're right. But the cool thing here is that we're looking for heat transfer, which is in watts, the same thing as power. And we can find the power supplied to the fridge by looking at the volts and the current, which are stated very clearly here. There are 115 volts and 8.5 amps supplied to the fridge, but that's at maximum power. So, because power supplied is volts times current, the maximum power that can be supplied to this fridge is 977.5 watts. Exactly. So, knowing that, we can find the heat transfer coefficient. How do we do that? Well, we use circuit analysis. Because when the fridge is plugged in and the temperature isn't changing, it's steady state, which means that circuit analysis can be used. And circuit analysis says that the temperature of the inside of the fridge goes through a resistance network that has to do with conduction, then reaches the temperature on the outside of the fridge, and goes through a resistance network related to convection, reaching the ambient temperature out here. Ooh. And so we have to find the thermal resistance of the conduction and the thermal resistance of the convection. For the thermal resistance of the conduction, we use the formula of the length that it travels through divided by the thermal conductivity times the area, all out here. And that equals 1.951 Kelvin per watt. That's right. And for the convection out here, the formula is 1 over the heat transfer coefficient times that same area. But since we're solving for the heat transfer coefficient, we can't solve that one quite yet. And the total resistance will be the sum of the conduction resistance and the convection resistance. So under the ideal conditions, the maximum power supplied is 977.5 watts. And using the circuit analysis, we see that heat transfer is equal to the ambient temperature minus the temperature in the fridge all over the total resistance. But because we're also looking at the temperature applied to the power supplied to the whole thing, we need to factor in the freezer as well. And so the first one will be added to the temperature of the ambient air minus the temperature of the freezer over the total thermal resistance. And when we add those two together, it equals 2 times the ambient temperature minus the temperature in the fridge minus the temperature in the freezer, all over the total resistance. And so we say that the maximum temperature equals, or the maximum heat and the power supplied equals all of that. And when we solve it all out for the heat transfer coefficient, we find that it equals 0.5173 watts per meter squared Kelvin. Wow. So that has to do with the air leaving? Yep. That's what affects the temperature from the outside of the fridge to the temperature that we feel here. So, knowing all of that, we can then know what happens after the power is lost. Because at that point, the temperature will begin to change. It's no longer steady state, which is called transient, which means the temperature changes with respect to time. Because of that, we need to know the Biot number. The Biot number is a measure of convection versus conduction, and it's a ratio. So because of that, it can tell us whether we can use some certain easier analyses. And even if we can't, they'll just be a little bit more flawed. So with the Biot number, it's the heat transfer coefficient times the length all over the thermal conductivity, and that gives us a dimensionless number. In this case, it'll be equal to 0.536. But in the case of the lump system analysis, which is what we'd like to use to determine whether an entire object can be modeled as something with consistent temperature all the way through, we would want it to be closer to 0.1. Less than would be preferable. And because it's a measure of convection versus conduction, the smaller number would mean that conduction, which is in the denominator, would play the bigger role. But because ours is 0.536, which is quite a bit greater than 0.1, we know that convection plays a bigger role than lump system analysis typically takes into account. So if we were to use it, it would have a high error. But we just want a general idea of how this works, so it'll be okay, right? Yeah, absolutely. We just have to take into account that it won't be hugely accurate. It's just that convection plays a bigger role than we can take into account. So, using slightly flawed lump system analysis, we can represent the entire temperature in the fridge and the freezer as an average of the two, and that'll make the whole thing a lot easier. So we say that the initial temperature is equal to 261 Kelvin, which is the internal temperature of the fridge, and plus the internal temperature of the freezer divided by 2. And the final temperature will be the earliest temperature in which the bacteria can actively and easily grow, when the food can easily spoil. Exactly, which would be 277.4 Kelvin. And the ambient temperature, the 90 degrees Fahrenheit, is 305.2 Kelvin. That's right. And because we determined that the Biot number is 0.536, we will estimate it to be about 0.5. And remember that table I showed you a while ago? Oh yeah! What we do is for the Biot number, we can determine a few different things. Because for lump system analysis it can be a bit complicated, we need to find some special values that can only be found very difficultly, and we don't really want to do that because they're already online. So we'll look up the characteristic eigenvalue, or the first one, which is 0.653 for the Biot number of 0.5, and the first arbitrary constant A, which is 1.07. Ooh. And we can plug those into the lump system analysis equation, which is the final temperature in which the food will spoil, minus the temperature out here over the initial temperature that we started with, minus the temperature out here again, and that all equals the arbitrary constant A times e to the negative first eigenvalue squared times the Fourier number. Well, what's that? That's another calculation that we have to determine. But for now, we're going to solve for that. Plugging everything in, we determine that the Fourier number equals 1.245. And because we're using lump system analysis, which is a non-dimensionalized equation, we don't have any units. It seems like it could be easier, but sometimes it just makes the calculation harder. So we always want to double check. Now, we look at the Fourier numbers equation, which is equal to the thermal diffusivity times the time divided by the characteristic length squared. And the characteristic length is just for a flat plate, 1/2 of the length that we determined earlier. So it is 0.0254 meters. Now for polyurethane foam, we're going to need to go back and look online again because we need the density and we need the specific heat capacity. Ooh, okay, I can find those. The density is between 24 and 40 kilograms per meter cubed. So we'll find an average as 32 kilograms per meter cubed. And for expanded polyurethane, the specific heat capacity is about 1600 joules per kilogram Kelvin. Perfect. Plugging that in to find the thermal diffusivity, which is thermal conductivity divided by the density times the specific heat capacity, we see that it's 4.785 times 10 to the minus 7th meters squared per second. And plugging the thermal diffusivity into the Fourier equation, we'll solve for the time, and we can determine that the time is 66,087.8 seconds. Wow, that's 18.36 hours. That's right, but remember, you have to factor in the error. So it'll last about a day without opening the fridge or freezer. Yes, it'll maintain a safe temperature without the food spoiling for about 18.36 hours. So we have a day. Just a day. I hope the power comes back on before then. Don't worry, it will. Okay. Did you turn it off?